Hello, class. This will be a continuation of the probability lectures from section 5.3, conditional and the multiplication rules. And we're going to add a new definition, which is to talk about that multiple events, specifically two events, are independent or not. And so the definition is that two events are independent if the occurrence of one doesn't affect the probability of the occurrence of the other. And sometimes these are a little tricky to figure out as well. Hopefully these two are reasonably obvious. And the first one says that the college student is chosen at random. The events are being a freshman and being less than 20 years old. So these events are not independent. If the student is a freshman, the probability of that student being 20 years old or less, or is less than 20 years old is greater than for a student who is not a freshman, for example, a senior. Where on the other hand, if you're born on Sunday and taking a statistics class, they have nothing to do with one another, right? There's no effect. Being born on Sunday has zero effect on if you're taking a statistics class or not. So those would be two independent events. And how this ends up sneaking into the calculation scene here is here's the definition of how do you figure out if two events are probability independent. And what you do is you take the probability of ANDing them together, that they both occur, A and B together. If it equals the probability of each single event multiplied together, A times B, then those two events are independent. And when you do that calculation, and we'll get back to that shortly. So I'd like to do that definition first, and then I'd like to come back to this one. Look at that. So this is the general rule for multiplication of two events calculating probability. And you can see that we have the probability of A times the conditional probability of AB or BA. So where did that come from begin with? Well, I know I don't like to do too many proofs at all, but it's good to take a look at this. So this was our original definition of conditional probability. It was the probability of A and B divided by the probability of A. And you can see that if we do a little bit of algebra by multiplying both sides by the probability of A, it ends up being this, right? Probability of A and B equals, say if we multiply each side by probability of A, these cancel, right? So that's this equals that. And then we could say the probability of A times the probability of B given A. So if we go back and look at our equations here, you could see that it matches, what do we have here? I think it's the bottom one with regards to what we have up on the whiteboard. And so when we do, or the top one, excuse me, what we have up on the whiteboard. So when we do these calculations, if two events are dependent, remember the probability of A and B equals the probability of A times the probability of B. I know I don't like to do too much algebra and stats, but this is kind of important. So if you look at this, if two things are independent, That means the probability of A times B equals the probability of A times the probability of B, right? So you see, if I rewrite this, you can see that these A's would end up canceling if I divide each side by P of A, right? So if two events are independent, what's interesting is the probability of B is the same as the probability of B given A happens, right? Because A is not supposed to affect B if they are independent. This would be, what's the probability of you taking a stats class given that you were born on Sunday? It's just the same as the probability of you taking the stats class. So this makes these calculations kind of challenging, right? Because you have to deal with that part of it. So first of all, trying to figure out if something's independent or not, they can't actually have an effect on one another. And remember in our previous lecture, we had the table calculation. And typically when you have those table calculations, you'll see that everything's dependent on one another. There was a dependency of a woman and in degrees and men in degrees, et cetera. And so you'll see that that would occur as well. So let's walk through a couple more calculations here, and let's start with this one. And this one's a little bit challenging. So this says, among those who apply for a particular job, the probability of being granted an interview is 0.1. And among those interviewed, the probability of being offered a job is 0.25 or 25%. Find the probability that an applicant is offered a job. So what do we do with that? So the way to think about that, and I'm just going to pull up the whiteboard because the way they calculate it, I think is a little bit confusing. So the way you think of the way this is what is the probability of offered a job? I'll just call it offered, right? Given an interview, right? Because you can't have a job offer unless you got there for an interview, right? So remember, if we look at this calculation, this would be the probability of offered an interview, right? And that means you got a job, divided by what? The probability of you having an interview. So we're giving the following, right? The probability of granted an interview is 0.1. And the probability of offered a job given an interview, right, is 0.25 or 25%. So how do we calculate that you were offered the job? Well, that would be this, right? You were interviewed and offered the job. So that would be the probability of offered the job. And obviously you were in the interview. And we did this a little bit algebra before, so it looks like this. Times the probability of being interviewed. So when you plug those in, you get 0.25 times 0.1. And so that would be 0.025, which is 2.5%, which is quite small, but there was only a 10% chance of you getting an interview to begin with. And so that's why the aspect of the probability here would be very small. And the book calls this an unusual event. Remember we talked about that in the last lecture, a couple lectures ago, or I call it an unlikely event. Anything under 5% is an unlikely event. So here's an example of some calculations where now the events are independent. or obviously getting an interview and a job offer are dependent events. These are independent. And so this says that ages of people under the age of 18, 23 and a half in New York, 25.8 in Chicago, and 26 in LA. So if one person is selected from each city, what is the probability of them are under 18? And here's this unusual event. I would use the word unlikely. And so these three events are independent. You can't live in New York, Chicago, any of the two cities at exactly the same time, right? And so if the probability of these events are independent, it's nice because it makes the calculation a little bit easier. So what we're trying to do here is what is the probability that all of them are under 18? So basically, you're looking for the probability that are under 18 in New York and under 18 in Chicago. I'll just put a little 18 there. And under 18 in Los Angeles. And since they're all independent events, we could write it this way. The probability of under 18 in New York times the probability of under 18 in Chicago times the probability of under 18 in LA. So when you do that, we're given all three of those numbers. So you just multiply them all together. I'm just reading them right off the slide. Again, these slides will be uploaded as well. You could take a look at them. And when you do that calculation, you get 0.0158, which is about 1.6%. And is that unusual? Well, it's unlikely, but the book uses the word unusual. And again, the criteria, is this less than 0.05 or 5%? The answer is yes. So it is unusual. Okay, so I'm just going to keep going here. This might